This episode of Hak5 is brought to you by Domain.com.
Hello and welcome to Hak5. My name is Darren Kitchen. And this is a Mike Ossmann. Mike, welcome to the show. Dude, it has been, so long since you were here in studio. The last time we were talking about the Jawbreaker.
Yeah, and it wasn't here in studio, it was at a different studio.
Right, so it has been way too long. And of course, Mike is on a very special mission to keep us in focus and provide stickers.
Stickers, yes!
So Mike's idea is to start a new sticker wall, or maybe it was Shannon's, but.
That's my idea.
All right,
Yeah,
Shannon's saying it was hers. And I guess we're gonna do just that. So
All right.
Thank
Pick
you.
a sticker.
We're gonna go with the Great
Put it on the
Scott
wall.
Gadget hardware for hackers.
Excellent.
Nice, get you right there in the corner.
Wow.
Boom.
Inaugural sticker.
All right.
New wall.
548 Market Street, 39371, San Francisco, California, 94104. Send the stickers. But we're not here to talk about stickers today. We're here to hack some RF. It's such an appropriate named product, isn't it?
Hak5, yeah.
Well, we've been having so much fun with your new Yardstick 1, which everybody should go out and get, because Mike did an amazing job putting together a CC11K. Or is the K important? I guess that's just on the
It's
dev
a
edition.
CC1111.
Okay.
It's just a CC1111.
And if you would want to recap that for anybody that's new
Sure.
to hacking sub 1 gigahertz.
Yeah. So Yardstick 1 is a radio dongle, and it's basically a digital radio modem on a chip. So it allows you to take various radio systems, mostly low-speed digital communication systems below 1 gigahertz in frequency, and interface with them very easily. And it's not really a software-defined radio. People kind of know me for software-defined radio stuff like Hak5, but it's a software-controlled radio, and it's very easy to use, and that's why I like it, and that's why I wanted to come out with this product was to make a device that was very easy to use. The learning curve for SDR is steep. It's rewarding, I think, for people to learn SDR. In the long run, you're going to be able to do more things with software-defined radio. But if you want to get something done quickly and as easily as possible, for many applications, it's easier, at least in part, to use tools like Yardstick 1 using RFCat and other tools that might have a wireless transceiver chip as opposed to software-defined radio.
Right, and it makes it as easy to hack with sub-gigahertz stuff that say in the similar sense, have you played with the ESP 826s or whatever?
Right.
And you can just hit them with AT commands over a serial connection. It's kind of in the same vein. You're not interfacing directly with the radio, you're telling the radio what to do.
Exactly, yeah. You're controlling the radio from software. Same thing, Ubertooth. It's the same type of architecture, right? So if you have a 2.4 gigahertz kind of solution that you're trying to probe, and it's using Bluetooth or anything that's vaguely like Bluetooth, you can use Ubertooth instead of using software-defined radio. There are two different types of tools, those wireless transceiver chips versus software-defined radio. Software-defined radio is far more flexible and powerful, but oftentimes the wireless transceiver chips are easier to use for a given application. And that's why I think it's beneficial to have both kinds of tools in your toolbox.
Well, we're going to be using both tools today, in fact, because you brought some fun things to hack on that I think everybody should have some experience with, especially if your parents have liquor cabinets with one of these.
Yeah. So this is a cabinet lock, a wirelessly controlled cabinet lock. And so that gets installed in a cabinet or a drawer
I
or
see. So
something
you just
like that.
screw this into the side and then.
Yep, and then this little
This gets
tab.
screwed in.
It's in a locked state right now, so you
Oh,
can't pull
so
that
I can't
out.
pull this out.
But if I enter the code,
But I want the booze.
Let me enter the code on the keypad.
Okay.
Here, GSG rules, and then I hit the unlock button. It totally didn't work. One more time.
Okay.
I really should use a shorter password. There it is.
Aha!
There was a little click there before you pulled that out. It was unlocking.
I got to the booze. Sweet.
Yeah.
Okay, and then similarly, so you want to show that to the other camera so that we can actually see this keypad. It's kind of interesting.
Yeah, it just has a bunch of numbers and an unlock and a lock button. And nothing happens until you hit the lock or unlock button. You enter in a numeric code, and you hit the unlock or lock button, and then something happens.
So it's keyless entry in a similar way to what we've been talking about with key fobs and that sort of system.
Right, it's very similar to that, except with a keypad that allows you to enter a code. And I'd like to kind of go through an exercise where we use both the Hak5 one and the Yardstick one to try to reverse engineer this thing as rapidly as possible.
Okay.
Because I find that it's very handy to have both tools at your disposal. Some things are easier to do in one type of tool, some things are easier to do in another type of tool.
Well, let's get to it. What's the first step?
Well, the first thing I usually do, of course, is look up the FCC ID.
Yeah.
Right, so the FCC ID on here.
Actually, I believe it's, if you had physical access to the liquor cabinet already, you can see the FCC logo there.
Yeah, but if you don't, you at least have the number on here. And actually, there is an FCC label on here, but there is no FCC ID on this device.
But because this is the receiver, it's not an intentional transmitter.
And
that device is.
That's actually a really important point, that if you see a pair of devices like this, and one of them has an FCC ID and the other one doesn't, that is a very strong indication that the one that has the FCC ID is a transmitter, and the one that doesn't have the FCC ID is a receiver. And therefore, it's not bidirectional communication. So
that's the important part, because people keep bringing this up as we've been delving into hacking rolling codes on automobile key fobs, as people are saying oh, well, how does it know what the code is supposed to be? Well, obviously they go back and forth. It's no, they don't.
Right.
The car's not transmitting back to the fob.
Right. Except on the passive systems, but in the standard remote keyless entry systems, that's absolutely correct. It's a one-way communication, and this is a very strong indication. Just seeing that we only have an FCC ID on one of these devices tells us. It doesn't tell us with 100% certainty. Sometimes things don't follow the rules, but it's a very strong clue that this is probably one-way communication, and we're only going to see transmissions come from this device. So let's look up the FCC ID that's on here. Are you on fcc.io by any chance?
No, I'm actually not. I don't have my laptop hooked up to the system. Do you?
No, I'm not on the internet.
Oh, fantastic. Well, hang on. Let me grab this magical HDMI cable from off screen, and then everything will be wonderful.
I hear there's this place called the internet. I'd like to see what's there.
Oh, okay. Well, if I just pull up my screen here, I can now go to, where am I going?
fcc.io.
fcc.io / the FCC ID is VCRTP-100. Takes you right to it. All right.
FCC.io is a cool website. It was created by Dominic Spill, who is the lead developer on the Ubertooth project and is active in Hak5 and Yardstick 1 and so forth. And he put together this really cool tool that everybody should know about. Super easy to look things up. And one of the great things about FCC.io is it gives you an easy way to share URLs for FCC filings, because the FCC website is horrible for that.
Well, they just redid it actually just 2 months ago.
That's
remember?
True.
And then you couldn't do anything you couldn't file anything, and everything was broken, and it was terrible.
Yeah. So anyway, let's take a look. And I just want to look briefly.
Yeah, summary or the details?
The main thing I want to look is right here.
Oh, was it right there?
It was right there on the right-hand side of the screen. It says 315 megahertz.
Oh,
I'm not even going to look.
What isn't 315 megahertz when it comes to sub-gig hacking?
I know. There's
a
lot of stuff at 315 megahertz. There are tire pressure monitors. There are garage door openers. All sorts of remote keyless entry systems. But sometimes you see things at 300, at 390, at 433.
So now we're entering the Internet of Things, where everything is Z-Wave or Zigbee. Before there was the Internet of Things, you can think of it as the dial-up of things, and everything was 315 on-off keying.
That's an excellent point. The dial-up.
The dial-up of things.
I like that.
It's we have to apply it after the fact. It's like the Stone Age. You didn't know you were in the Stone Age until we were out of it.
I might need to use that.
Okay.
Things. So, so we should expect to find this thing at 315 megahertz. Now, of course, there's a lot more information we could find if we dug into the documents, but for now, let's just go with that. Let's see what we can find at 315 megahertz.
Right.
And at this point, this is where I like to turn to software-defined radio, like Hak5 or like a Realtek dongle, or any kind of a software-defined radio platform.
We've just been using these to sniff. They're great.
I've got a Hak5 plugged in here.
Sweet.
So I'm going to run Ossmann FFT, which is a favorite tool of mine. It's really simple, and it just talks to the Hak5 and gives you a real-time FFT.
Oh, that's cool. That's the FFT right from within GNU Radio, and you just called it from the command line.
Exactly. This is just a something that you could do by throwing together a flow graph in GNU Radio Companion, but it's a ready-made tool that you can call from the command line. So let me just tune this to 315 megahertz and see what we get here. I'm going to enter in my code and try to lock or unlock it. And did I get something? There we go. Definitely something. If you hit the peak hold, then you can see very distinctly right by that big middle finger. You should see something else happen, a much higher peak. And it's really high because I'm holding it at very close range. Now, one of the things I like to do, and one of the great things about Ossmann FFT, is that it has this little record button in the lower right-hand corner. And so in addition to just tuning around and adjusting the bandwidth and adjusting the gain, you can also, when you find a signal, just hit the record button and save the samples to file. And it's saving the raw.
Yeah, I was about to say, because we've been recording with GQRX, which is really convenient because then we get a nice little WAV file. We can open it up in Audacity.
It is.
We've run into some trouble when we want to systematically decode that data.
Right. And I see people do that a lot. They use GQRX or some other type of tool that gives them a record function that records, or it saves to disk, the demodulated waveform. But you might not have your demodulator in that software configured in the right way for the type of signal you're looking at. What's great about Ossmann FFT is that its record function saves the raw INQ data, the actual data that comes over the USB from Hak5 or whatever platform you're using. The raw radio waveform is being saved instead of a demodulated interpretation of that waveform. Now notice that nothing happens when I push these numeric buttons, and we can observe that very easily. Until I then press the lock or unlock button. I have to press 4 to 8 numerals, and then I hit the lock or unlock button, and then it transmits something. So apparently what I need to do, if I want to get a nice, concise capture file, is to go ahead and
pre-buffer those in there.
You're right, exactly.
We don't want a large recording with a bunch of noise. We want just a snippet.
Enter 1, 2, 3, 4, then I'll hit record, and then I'll hit the lock button, and we'll see what I get. I'm recording. Now I stop. Now let's go take a look at that file. All right, so I exit Ossmann FFT, and if I take a look, I have this file called /temp/something or other. It called it name blah blah blah. I could have adjusted this name in the GUI, but the default actually encodes a bunch of information in here that's kind of handy to see. It tells me that it was captured at 3.15 times 10 to the 8th power. And so forth.
315 megahertz.
It gives me, it was captured at 315 megahertz. It was captured at 8 million samples per second. It gives me the date code. So even though I didn't change this name part of the file name, I at least get a bunch of metadata encoded in the file name, which is kind of handy if I want to go back and see. So I'm going
Sounds way better than ASDF, GHJK. Not like anybody here is guilty of naming files like that.
No, who would do that? So let's see, I captured one earlier, but this is the one that I captured just then. And I'm going to open it up with a new software tool called InSpectrum.
Ooh, InSpectrum.
It's brand new.
What does InSpectrum do?
It's very new. It's very young. It isn't very sophisticated yet.
Okay.
But it is a handy tool that you can find on GitHub that is made by a friend of Hak5 and Mike. It's spelled M-I-E-K.
Oh, Mike.
He's often in the IRC channel.
Totally. Yes, I've seen him on IRC, and I've seen his work on. In fact, it's on our list of. I saw it on GitHub. This exact tool. We were going to show it off.
We're doing it right now.
There we go.
Okay, so here we have this
Oh, but this
spectrogram.
it's like a waterfall, but it's not live.
Right. You can go back and look at what happened in that.
There's the lady in
period
the
of
red
time.
dress.
Yes.
Totally saw her go by. It's true.
Notice the default sample rate is 8 million, which happens to be the default sample rate in Ossmann FFT, so I
Nice.
didn't have to configure that. But it lets you change a couple of options and like zoom in and out and stuff. But what I'm going to do is just scroll down until I get to some big event. Hey, look at that.
Hey.
And then I can scroll and see what was going on there. Now you'll notice that.
So this is it's kind of similar to what we were doing on Audacity, except we actually have all the data this time.
Right. So regardless of what modulation was used, we've captured the entire event, actually in a form that we could replay without even knowing how to demodulate it. That's a fun thing to do with SDR, but I'm not going to do that right now. I'm just going to use this in Spectrum to inspect the spectrogram and figure out what was going on here. If I zoom in a little bit, the zoom goes vertically. And you can see that right next to my DC offset, which is that green line down the center, there are these bursts going on. And it happens to be really close to 315 megahertz. If I increase my FFT size, you'll notice that things get wider horizontally. And I can start to actually discern a difference between the stuff that's happening at this frequency and the stuff that's happening at this frequency. This frequency is my center frequency, so that's where I was tuned to, 315 megahertz. So this is just below 315 megahertz, and that is the signal that was being produced by our little keypad here. And you can see, you see how there's sort of a very consistent frequency that goes out, right?
It's
what does
just
this look
dash,
like?
Dash, dash. It looks like on-off keying.
Looks like on-off keying, exactly.
In fact, we can see some that are longer and some that are shorter, some gaps.
Yep. And notice it starts with a very consistent pattern, or it's at some kind of a preamble.
Like just a clock. What is it called? We were just talking about it last week.
I would call
a
it
sync clock.
Yes. I would call it a preamble. Although notice that unlike some preambles, it's not on and off for the same period of time.
Okay.
See how it's kind of long pulses separated by short gaps?
It's like DAS instead of dots.
That's a little bit different than you might see in some systems, but you never know what you're going to get. But in this case, we seem to have on-off keying where we have a lot of long pulses to start the packet, and then we start seeing some short pulses, and notice that the short pulses are followed by longer gaps. And then we start seeing various short or long pulses. Every pulse seems to be either short or long. There are two durations. So this is probably pulse width modulated on-off keying, where we have short pulses representing a 1 and long pulses representing a 0, or vice versa. We don't know which, but it's
as
easy
opposed to the amplitude shift keying stuff that we've been working with.
Okay, and well, although I would call this a form of amplitude shift keying, except that it's pulse width modulated, and so it's whether it's a 1 or a 0, whether the data bit is a 1 or a 0 is encoded in the length of the pulse.
Okay.
The one thing you may notice is that the duration from the start of one pulse to the start of the next pulse is very consistent.
Yeah.
And if we look kind of closely,
so it's almost like there's like a constant rhythm that it speaks.
Exactly.
Is a way to think of it. Whether it's a short pulse or a long pulse, the time between those is always going to be about the same. Right?
Yep. And if I turn my FFT size down, I actually get like I no longer have the ability to like tell the precise frequency, but as well, but I get better resolution in the time domain. I have there's time on the vertical axis, frequency on the horizontal axis, and by adjusting my FFT size,
it doesn't seem to be moving around frequency-wise.
I get to so I don't need to really pay attention to that. I can turn my FFT size up if I want to see more frequency information. I can turn my FFT size down if I want to see more time information. So if I turn it down, I can see more precisely how long these bursts are. And you can use the ruler on the left-hand side there to kind of figure out, and
the actual milliseconds.
You can eyeball this and see basically like there is a unit of time. And a short pulse is 1 unit, followed by a gap of 2 units.
I mean, everything uses time units, even
Right.
Wi-Fi.
A long pulse is 2 units long, followed by a gap of 1 unit. So everything's in these 3 time units. And so if you were to interpret it as a basic amplitude shift keying, a long pulse would look like 110, and a short pulse would look like 100. Right? You see what I mean?
Right, yeah.
If I call a symbol one time
So
unit.
if we guessed, like, okay, to make that hypothesis, how can we systematically now take this data and test that theory and see, oh, well, does it give us, I don't know, like a normal unit of bits? Like, do you get 64 bits out of this or something common?
Right, and this is the point at which everybody, if you've used SDR, this is the point at which you've said, oh, okay, it's really easy to get to this point. How do I get to the next point? How do I? And now I've figured out how the information.
I have data. I should do something with it.
How do you get from the waveform to bits? You can see the
you
bits.
Get graph paper.
Yeah.
And Sharpies, and that's how you make really nice looking presentations instead of PowerPoint. No, that's what Mike does.
Yeah. So you've had the experience of struggling with getting from the waveform to bits, and in particular, you've run into problems with clock recovery. Have you not?
Yes, I have. Well, GNU Radio is awesome in that one of those modules, that clock recovery, should, if you filter it the right way, if you send it the right signal, it should be able to spit out bits. And I just saw a great paper that you did with. Help me out here. I can see their logo, but I can't remember their name. Anyway, another security vendor on doing exactly this.
I don't even remember what you're talking about. But
oh, okay. Well, they said you were instrumental in the paper.
It's something that I've worked on a lot, and everyone who's ever done digital reverse engineering with software-defined radio has struggled with clock recovery.
Yeah.
Well,
I guess it's a very picky beast. It seems to only want delicious packets, and if you feed it like undelicious packets, garbage is going to come out.
Right. You have to figure out. You have to learn how to kind of massage your input to a clock recovery algorithm so that you set it up for success. But we're not going to mess with any of that today.
No, we're not going to take all this IQ data and squash it down and feed it into the.
I'd love to teach people how to do that, but it takes many hours. So that's what my SDR video series is for
Which I was going to mention.
Right?
We were talking at the talk about how the differences between the yardstick versus Hak5 and how you can do everything with software-defined radio.
Right.
It's just a little steeper of a learning curve. But you've made that a lot easier. So I was going to save it for the end, but let's just plug it now. You guys should stop watching Hak5 right now and head over to Mike's site, because you're doing some awesome tutorials with on the Great Scott Gadget site about.
And we're getting there.
Radio theory, all of the stuff.
We're getting there. And then there's also videos that Shannon's done. And I mean, lots of people are trying to help you learn SDR. Everyone. But it is a steep learning curve. There's a long way to go. Even in my video, I'm 10 videos into my video series, and I still haven't gotten to clock recovery yet. We'll get there, but I'm not there yet.
Yeah.
So, but what I want to do today is turn away from SDR briefly.
That's the nice thing about these, is you can start going straight into the practical.
Exactly.
I know how to write Python.
Right. And if you're reverse engineering a system like this, the SDR platform like Hak5 is fantastic for finding the signal, recording the signal, analyzing it, determining the modulation, determining the data rate, which I'm not going to do right now, but you can use the ruler right here on the side of the screen to figure out what this unit of time is here. And it turns out there's 2,450 time units per second. So
we've got a bit rate.
We've got a bit rate.
Okay.
Once we know a frequency and a type of modulation and a data rate, we can turn to a faster, easier to use tool like Yardstick 1 for the next step in the process.
Let's do just that. Now, I want to thank Mike Ossmann for joining us in studio. We're having so much fun, and we will pick this up tomorrow with part 2 of 2, because this is really exciting, taking what we've now done with the Hak5 and then putting it over into the Yardstick 1 with RFCat, and we're going to demodulate and crack this code. and break those locks. It's going to be so much fun, so I will see you tomorrow with that. If you have questions, leave them in the comments. And before I get going, I do want to thank our awesome sponsor, Domain.com. If you guys have been watching the show for a while, you know how much we love these guys. They're fast, affordable, easy to use, and they will get your website up online in no time. And getting started with Domain.com is a snap, whether you're looking for a new domain or hosting. And right now, I can't express how right now is really the most epic time ever to get yourself a new domain over at Domain.com, because they are having a big, huge, awesome, gigantic sale. HAK Jumbo is the coupon code. That's going to get you an extra 35% off new domain registrations. It's a limited time offer just between now and November 30th, so you really have to act fast. But again, Domain.com. Use that code HAK Jumbo. And you know what? Be sure to tweet some love at Domain.com for supporting Hak5 for so many years. And remember, when you think domain names, think Domain.com. For Shannon Morse and myself, and of course Mike Ossmann, we will see you, we'll see you tomorrow and again next week. Until then, trust your technolust.
So before we actually get into the setup and the demo, I do want to talk real quick about some of the differences between the Yardstick 1 and the other CC1111 dongles. So most